Hello, Hector.
Hello.
Hello. Hi, Yuri. Hi, Yuri. Good. So today, I think a lot of people have scheduled today. I think Maya is not joining. Also, Darren is not joining. So yeah, let me share the screen. Yeah, I see, Yakov, some of your questions for the book authors. You started putting them together.
Mm-hmm. I'm not yet making so much progress as I wanted, but I... And maybe
Okay.
some of these questions just you have to ask in the forum and to get answers as well, so I'm not sure how difficult they are.
Okay. All right. Okay. So I think maybe Srivnas, I don't know if he will join. But let's get started. So today we are going to continue with our book session, NLP with Transformers, chapter 8, which is making transformers efficient in production. The chapter started talking about the previous chapters was about, fine-tuning the models and getting a good result, which is really good what we need. But the big problem is that in production, big models, giant models will not be able to meet business requirement, right? Because we cannot take this big model and put them there. So the solution is one way, crude way, is to train a more compact, small models, but the performance will not be able to meet up with the big model. So the better solution is different techniques that we can mimic the accuracy and performance of large model, which is by one way is knowledge distillation, quantization, pruning, and these techniques basically speed up prediction and performance of our model. So that is what this chapter is about, to explore ways that we can speed up our model performance in terms of accuracy and other stuff, much the same like bigger model, but with small model. So they started also giving an example by a company called Robolex, I think. They basically scale BARD with a high accuracy. So we can see here, they started, this is, BARD baseline. And we can see that the latency here, we can see is, 330 millisecond, and the performance, the throughput is 100. So this is not really good. And now one way they did is they create what is called distal BARD, but with a fixed shape input. So what it means by fixed shape input, we know like we do some padding. So this is fixed shape input. And so we can see like distal BARD with fixed shape input, it gives us a good, better than the BARD. The next one is dynamic input, where dynamic shape, where there is no padding. You can see this is an example of text where here we pad, here we don't pad. And this gives us a good performance. So dynamic shape input with distal BARD gives performance. But what really makes a very giant stride and performance is not this, but what is called dynamic shape input plus quantization. So which is one of these techniques to make bigger models look, so this is what they started giving us inspiration from this paper. I think it's this paper, that this is dynamic shape input and quantization gives a great performance. So that's the motivation, what we want to see in the later part of the book. So before they continue, they take a task, which is for intent detection as a case study. So I didn't even know before what intent detection task is. It's only in this chapter that I was able to, yeah, so intent detection is just like given a text, you determine the intent for that text, and that is basically what it is. And in intent classification, you need to have what is called out of scope, which basically try to deal with questions that are out of scope. So here they give an example. What is my balance in this? How many sport teams doing? This gives us a wrong, and here it gives us out of scope. So the meaning that whenever you want to do intent detection, we must try to make sure that apart in our data set, we have what is called out of scope stuff, so that when there is question which doesn't relate to this intent, this kind of answer. So now the intention for this chapter is, to train, to have like a small model and compare the performance with big model. So the first thing is, let us have a baseline big model. So they train a baseline model, which is BART, based on this data set, based on the data set, intent detection data set. And they have like, when they fine tune it, they have like 94% accuracy on this data set. And now we can see here, the data set has like, 150 intent, 10 domain, different kind of domain. And it has like 1,200 out of scored queries, which belong to this class. Now here we download the fine tune model, the train on these data set. And now we try to make prediction here. We can see high, which is rental intent, right? And here we try another one. Here I'm coughing and have a fever. Yeah, it says this is a weather, right? So this model is really good. But if you look at this guy, this model doesn't know what is COVID, right? But the model know what coughing and fever is something that relates to weather, right? Because, so when we ask this model, do you have COVID? Then it says out of scope. So it means the model doesn't understand this and is making a good suggestion. But when we attach vaccine after COVID, then the model understands that this is, something related to vaccine. So the intention for this speaker is vaccine. So we can see here that the model, the out of scope actually making a good sense here. So that's about the fine-tune model they did on the task. Yeah, so anyone want to add something? Any question or want to add contribution? Okay, right. So now we have seen the fine-tuned BART model, the baseline model. Now the idea now is to let us create a very small model and now compare its performance with this large model. But before we create the small model, one thing we would like to do, the book started is doing is, is like creating performance benchmark. So what benchmark can we compare the big model and the small model? So they took three things: model performance, latency, and memory. So the performance of the model, when we compare the big model with small model, which is this, small model, how do they perform? Does the small model performs well like the big model? The latency, how fast? Does it have lower latency than the big model, or they have the same latency? Then the memory, can it be deployed? So trying to answer this question to compare with the model we create, they now create class performance benchmark here. And we can see here the performance benchmark here. We now create compute accuracy. We now compute size, then time pipeline. So we're gonna compare this model performance, latency, memory. So these are the functions that we'll use to do that. So this is basically what we see. So now before moving on, the presented discussion about the itself, the data set we will use, the Clink 150 data set. So the Clink 150 data set is basically a data set with different versions. So number one, they have full, they have small, they have imbalance, they have plus, and it comes from this paper, the data set. So this full, it means this is the full version, small is a small version, and the imbalance is the one with the imbalance and stuff like that. And now here, let's download the data. So here we download the data, and we can see here we put which kind of the data we want. So here, if we need the full, here we put full. If we need plus, we can put plus. So here we put plus. It means we want to download the data plus. So plus is a data set which is full with plus with out of score stuff. So this is different kind of data sets. And looking at the data set, we can see like it has this train, validation, you know, just normal Hugging Face structure. And now here we can see sample. We have the intent, you know, can you call me a different name? But we can see the intent here is an integer. So we can basically change the intent to, we can convert the intent into, you know, text. So that is the data set that we have seen. So this data set that we're gonna see to train small model and compare its performance with these very large models. So, but some of the performance stuff that we said we compare accuracy, the compute size, the size, the latency, and the pipeline, the time. So we have not implemented them here. So here they want to implement each of them. So here they want to implement like the first one, which is compute accuracy, to which will basically calculate the accuracy of our model. So this is this. Then the model size, which also hasn't been implemented. So they will implement the size of the model. So we can see here, this is the function compute size that will actually compute the model as well. Then the time, how long the latency also will be calculated. So here they are using what is called path counter to calculate the how long the model takes. Now here, this is just an example to show us what happened. So here you can see we want to implement some kind of counter here, which is just a bug counter. But we can see like here, it's doing the same thing, but it's giving us different value, right? So the first counter, the time it takes is this, second one is this, and the third is this. So it means that latency it's giving us doing the same thing is somehow variable, you know? So we can see that it exhibits some kind of spread, you know, different. So the idea now to calculate the latency is to maybe do some kind of loop and now calculate the average. So this is what they said. We will collect the latency over many runs and then use the resulting distribution to calculate the mean and standard deviation. So this is the you know function that calculate the latency for that. And here we can see we calculate the average and also the standard deviation. And now here we have the time pipeline return when we call this stuff. So we can see now here all these three things that will be used to compare the performance of the models have been implemented. That is the time pipeline and the size of the model and the accuracy of the model, which will now be used to do that. So now all the functions have been implemented in this class. Now let us give it a spin to see how the model works. So here we want to get the performance of our fine-tuned BART model on this data set, clinic data set. And now here we, we run this and now run the benchmark. So we can see here in this function, this class, we have the run benchmark. Yes, so we have this run benchmark, and here we all define this one here. So when we call this, this will run the metrics, right? So here, this is what we call. Yeah, so it returned the metrics. I don't know, it's supposed to return model size, average latency. Is it all? I don't know. Oh, okay. No. We have size, the time, the latency, the accuracy, but I can see only two. I don't know what's happening here.
I think it's printing not the output of the run, but print statements inside the functions. And it's quite possible that the functions, so if you scroll up, maybe you see that they print out the values to the standard output, and maybe the accuracy does not do that.
Okay. Yeah. Anyway. Okay. So yeah. So now we find the benchmark here. Okay. Yeah, I understand. So we find the benchmark now for the baseline model, which is BART model, and now we will compare. We will now start creating models, small models, and when we create them, then we can compare the performance with this model. For example, here we can see the size is this, and now the latency is this. So one of the way we can do that is called knowledge distillation. That is one of them approach. We have quantization, we have all those. So knowledge distillation is basically a method in which we train a smaller student model to mimic the behavior of big giant model, with the intention maybe it can have similar performance. In some cases, maybe we try to have better performance. So let's look at knowledge distillation. First, before that, let's go back and look at how when we train a model, what happens. So this is kind of normally what we do. For example, we do classification. We have at the last, we have softmax, right? So here we have softmax, and now the prediction here, the softmax, because it's log likelihood stuff, so it will give the highest probability this value, right? And now we have the actual stuff here, which is basically when we want to have the prediction, we have a classifier at the end. Now, if you look at this predicted and this actual, it turns out that this predicted contains much information than the actual, in the sense that this value with this value with this value, there is some kind of relationship between this value. This is telling us that this may be, but this class is closer to this class. This class is closer to this in some sense, because you can see this one, like, it has this and this is that. But if we take this, which our bigger model give us this one, this does not contain any information. So this is what we said, the predicted has rich information, and we use the predicted to teach a new model. So since this prediction has some kind of information that there is relationship between these guys, we can use this information to teach a new model. Because this complex model, it does with very complex model, and it learn this. So can we use this learnable stuff to teach a model so that it can learn from this? So we can see predicted tells more information, and we can use to teach a new model, but the hard level cannot teach any model any similarity, because here when we have this is 100, which called the hound, they cannot have any, cannot teach anything. So we're gonna maybe concentrate on this to teach a smaller model. So here I like images to, walk through something. So here, this is some ways to visualize the knowledge distillation. So we have a data set, and now we have a pre-trained model, which is a teacher in some ways. And now we do some train the models, and now we have the predictions. We train the same data set on student and have some prediction. And here is true levels. So here there is something called distilled knowledge, where I made mention this guy, this stuff is now distilled, and now do some kind of mathematical stuff to find the loss and compare with this, and now do back propagation, and now retrain with this loss, we now retrain the student, but the teacher is not trained again. The weight are not updating in this case. We only update the weight for the student. So let's see what happened. So what is happening here, you can see, like, for example, we have this as the layers, we have this, and here we have the softmax here for the pre-trained model. Here for the small model, we have two things. We have softmax as well. We have softmax here. But here we have what is called soft prediction. And also here we have soft levels. So we find the difference between the prediction of the small model with the, with the big model. This is called distillation loss. And now here, this is the real prediction for the student model, which is one. But the idea is this. Let's look at, we can see here with the softmax here, we said there is something called T. So what is this T, which is called temperature? Now let's look at how softmax, what is happening here. So if we look at this, let's assume that the output is this, of our output layer is this, before we apply the softmax. And now here are softmax, and these are the probabilities. Now the idea here is this. We can see like maybe 0.90, this is the predicted maybe probable class. But this class is, you know, because we want to make sure that the information between this class, there is a relationship, but this is large enough, but the relationship here is not, there is a big gap between this 0.01 and this guy. So can we trim down this value to be closer to these guys? So this is the idea. Now we use what is called a temperature, where this temperature is something that we divide with the value here so that we have them. In this is an example. So this is a temperature. So before we do apply the softmax, let's add them here. This is another example. We have, this is our logit. Before application of softmax, we divide by the temperature here, each one. So you can see here, when we divide by temperature equals to 1, which is still the same thing. But when we divide by temperature equals to 7, you can see the final value is 0.2, 0.2. So it looks like in the same range, right? So they share some kind of relationship, relativeness is there. So this temperature, it means we can use this to change the model and now learn more. So you can see the higher the temperature, the smoother the prediction. So this is the same example that it gives, the book gave. So you can see here we do our prediction, which is hard target. But when we apply the softmax T equals 1, we get the something. But when we apply softmax T greater than 1, we can see that this giant, you know, stuff, they become somehow similar, right? You know, good and great. Can you see that? Because in the hard prediction, good and great, they don't look similar. They don't, you know, but here you can see when we apply the softmax T greater than 1, and then this output, they are now normalized, you know, the distribution is smooth. And now the model, when we train a smaller model with this distribution, then the smaller model can really learn something, because it can learn that good and great, they looks, you know, somehow, you know, similar, and man and good. So to sum up the process of knowledge distillation, this is it. First of all, we take the logit for our final, this one, before applying the softmax. This is it, the final layer. We have this logit. And now we take the softmax with application of temperature. So here, before we apply the softmax, we use temperature. And now we get hard predictions and hard prediction. So what is hard prediction? From this example, we can see this is hard prediction. That is a true prediction, softmax equals 1. And now we also do two losses, that is soft target and hard target. So what is soft target and hard target? This is the soft target. Yeah. So this is soft, you know, you can see that. And this is the loss here. That is the loss with this in the big model, the loss in this one. And now find the difference finally. So we can see soft target, cross entropy for the student and the teacher, and the loss two, which is hard target, cross entropy of student, that is true prediction. And now the final loss, we find something like this, which the alpha here is hyperparameter and stuff like that. So this is basically how the knowledge distillation works. The main idea, I think the takeaway is that the knowledge distillation use temperature to, you know, normalize the distribution of the logit before passing to the softmax. And now we find the two losses loss one, which is a soft target, which is this loss, and we find the hard loss, which is this, and we find the final loss, which we calculate this. So this is what I understand about the knowledge distillation. So anyone can add something on top of this?
I had one question when I was looking at it. So they use the same temperature.
Yes.
Yes. On both sides. Have you seen, like, is there any reasons to use like different temperature for teacher and the student?
Yeah, good question. I don't know. Yeah. So I think I don't know. I know
they have to be related, right? Like you want to.
Yeah, so that they will not be diverge, right?
Yeah.
Maybe Yakov or Sylvanus, can you attempt?
I would say the following thing. The gain as the aim of the knowledge distillation is to build a small model which behaves outside exactly like the big model. And so you want to train it to give the same answers, not only for the hard predictions, so what is the right class, but also the confidence, where you say that if the big model is not confident, then the small model should also learn that it's not confident over here. And so, but in the end, we want it to produce exactly the same output. So that if the student is a really good student, then it should give the same output as the teacher.
Yeah.
And so you want that if the student has exactly the same output as the teacher, you want the loss to be 0. That's the goal. Now, if you look at the mathematics, you have the output of the student, you have the output of the teacher.
Yeah.
You do some transformations, and then you do the difference. So if you do the same transformation at both sides, then if the output is the same, then also the output after the transformation is the same, and the distance is 0. If you would have a temperature, if you have a different temperature, then even if the student would provide the same output as the teacher, you would still punish him for not taking into account your temperature difference. So the goal over here is using the same temperature is because you want, your goal over here is that the student produces the same output as a teacher. That's identical. So that you want, if they're both identical, then you want to give them a score of 100% good or a loss of 0. I'm not sure whether that answers your question.
Okay, good.
But by the way, when now I don't remember how training is done. So you train with different temperatures, right?
With the same temperature, I guess, right?
No. But can you? Oh yeah, I think they do hyperparameter optimization, right? Temperature.
Oh yeah.
Hyperparameter.
Yes, it's hyperparameter. Yes. But I think the temperature, you don't say like the temperature for the teacher and the temperature for the student different, right? I don't know. Yeah, I think the temperature is, as you said, is hyperparameter, but I thought we are doing the same hyperparameter for the teacher and the student, so that they may be on the same distribution and they will not diverge. I don't know. You want to add something, Yuri?
Yeah. So that was I think, yeah, I understand. So we want sort of match. We want to match at any given temperature.
Yeah.
Right. Okay. It's
Yeah. Okay. Yeah. Maybe in the book.
Right.
Okay. So now we have seen, I mean, the basis of how the knowledge distillation works. So the next thing is let us create a knowledge distillation trainer where we can train a knowledge distillation. To do that, we need to do a couple of things, as we have seen, because we have hyperparameters now, alpha and temperature. As we can see, this temperature, and we have alpha here. So we have the trainer, I think, is different. So the new, which control the relative weight of distillation loss, okay. And we fine tune teacher model, which is about a new loss function that combine the cross entropy loss and the knowledge distillation loss. So you can see cross entropy loss and knowledge distillation loss. Here, this is knowledge distillation loss, right? Because knowledge distillation here, we can see here, we have the student and we have the teacher. This is a loss. And now this is the hard target. So we need to find a new loss function. So this is what they do. So adding the new parameter, we just provide those, our alpha and temperature here. You can see this is hyperparameters, and later in the book, we have some kind of hyperparameter tuning, finding the base of this stuff. And yeah, and this one here, okay, okay. Okay, so this is a trainer here. We can see here we have extract the logits here, because we know that we extract the logit before we apply the softmax here. So extract cross entropy loss and the logit, and extract logit for the student, and subcom probability and compute the distillation loss. So here we compute the distillation loss and subcom probability, and now here we return the weight of the student. So this is basically the knowledge distillation trainer. But now, choosing a good student initialization, how can we choose model which is student to initialize? Because now we have seen we choose the teacher, which is BART. So one good thing they made mention in the book is that a good rule of thumb from literature is that knowledge distillation works best when the teacher and student are of the same type of model. So you don't just go and select one model differently and another one different model. They said for knowledge distillation, it works best if the same model. And so, for example, here you choose BART and Rovata can have different output in embedding space, and can hinder the ability of the student to mimic the teacher, right? So I think what we are trying to do is like some kind of configuration, as we can see here, for the student and teacher. We always trying to see that they mimic one another. So I was thinking maybe the temperature, we should give also the temperature the same with the student as well as the teacher, so that they can learn some kind of stuff. So in our case, we are using distilled BART, which is actually the stuff. So the next thing they did was basically, okay, this is just tokenizer to tokenize our text. Hyperparameters and metric for distilled BART. So here they want to talk about the metrics and the hyperparameter for the distilled BART we will use. So here we find the matrix here. This is the matrix that we will use for that. Here is the training argument here is defined. We can see we put all this stuff, the stuff for the training. And now here we finally define the student configuration that will be used in our training. So here we can see we provided all the necessary information. And here we can see we try to create the classification here. And finally here, we now have all the ingredient, and we can start training the our student model. So here, the first thing is we load the fine-tune teacher, which was already there. We just load it. And now let's train the student here. So we can see here distillation trainer, which what we already have. Yep, this is distillation trainer here. And now here we provide the teacher, the data set, and our matrix that we define in the book, and now the tokenizer we define. And here we can see we do the train here. And here, if you are in the code, it was giving me an error, I think. Also down the road in the part of the chapter, it was given some kind of errors. I'm not sure, Sylvanus, have you solved some of the errors at the part of the book? Because I saw you are also in GitHub in the book, at the GitHub. I don't know whether you solved the problem too.
No, the convert problem still exists, but as Mayank had posted in this case, if you put those 2 lines of changing the collator, and I don't know why they don't update the book or whatever to say that that's necessary, but you have to do that in order to get it to work.
Yeah.
This was the case for the previous notebook as well.
Oh, okay. Yeah, I saw the what they did, like I think in the PyTorch 3 what they said. I saw the author of the book, he said like they would bump into the book, but they haven't done so. But also there are some errors at the last part of the book. I saw it hasn't been, yeah. Okay, so here we can see like we train the student here, and we can see that we have a good performance here, right? And we can see like 92% accuracy for the student. But what was the accuracy for our teacher? We know from the beginning of the book, the accuracy of the teacher, which is bad, they fine-tuned, was 94%, right? So this is not a bad, this is not something bad, having like 92% for the student and that. But okay, here we push it into GitHub stuff and okay, now after we push into GitHub, we want to see, let's try to see the performance, some of the other stuff. Now here we just download it and fine tune it. And now here we can see, here we find the performance metrics. Remember, we defined this at the beginning of the book. And now we run this stuff. We can see here the model size here is this 25.5989. I don't know, like, is it the size, is it better than the?
Yeah, the thing that you kind of have to realize is in this case, they're keeping the alpha parameter to 1. So that means they are just using the Distilbert. They're not utilizing, and therefore the Distilbert model obviously is smaller than the BERT-based model. So the 92 they are getting is just from the Distilbert, because when you use alpha is 1, the second term of 1 minus alpha times doesn't apply. So they are not actually teaching anything to the student. They're just letting the student model do its thing. That's what is happening in this case. If you go up a little bit, then they say in the text that they are using alpha F1 before they do anything else.
Where is that, you mean alpha? Anyway, okay. So, yep. Right. So the size of the model is still reduced, right? Even though.
Yeah, it's not reduced as much as you're just using the Distilbert model, which is smaller by definition. It's a smaller model than the BERT-based model.
Okay. Okay, so here they want to okay, here they just want to visualize the performance of the models, and we can see here the accuracy and the big bar and this still bar here. We can see like this is something good, in terms of the latency is better, but accuracy, it doesn't reach the BART, but it's something good, right? So from the plot, we can.
Over here, one comment
Yeah.
I want to make is if you look at the graph like this, you see that. I just want to make a very short comment. You see that the accuracy goes down, but you have to look at the scale, so that it's not 0 to 100, so that it's 80 to 90, which means that the drop down is greatly amplified. But really, it's almost the same as 86 compared to 87, which is a very small gap. But you just have put the microscope on it, where you only look at the range from 80 to 90. So when you compare numbers, you have to look always on the scale. How what you compare.
I didn't even look at it. Yeah.
But the other hand, the scale on the latency is starting from 0. So it's a very common trick in statistics if you want to convince somebody about something which isn't right, to make a graph where you don't show the full scale. So you could say that. So you could say that you have two measurements which are really equal, but you make 2 samples and you get a difference from 1% of a sampling error, and then you draw a graph where you start from like here from 80 to 90, and suddenly you see 1% difference is like half of the screen, and you get a very good, very impressive presentation that your new method produces a substantial increase, but it's really just a rounding error, and you just have amplified it by cutting off the axis. So statisticians, when they see a presentation where you compare 2 things and you don't show the 0, but you cut things off, see that's not how you do things. But it's suspicious about what people want.
Okay. Right. Okay. So
okay, let's go.
Okay, so we can see here the smaller model significantly released in the latency, but the accuracy is just 1%. So yeah. Now, can we do better?
The other detail, which at least the other detail that I thought was interesting, even to Yuri's question earlier and stuff, is when the inference is done with the student model, the temperature is set to 1. So the whole temperature reduction or not reduction, but smoothing of the softmax is done only during training.
Yes. So you say like the smoothing is only done during training, right?
Yeah. So when you infer, then the temperature is 1, which is kind of a detail. They just mention it in a single line in the text, but it's kind of important.
Okay. Right. So finding good hyperparameters. So there are many ways you can find the hyperparameter, but the book says using Optuna allow us to find a good. So we know like in this distillation, we have like alpha and temperature, which are basically hyperparameters. So now the question is, how can we optimize them to find the best one? So they introduce something, an example where they discuss, let's find the value of X and Y so that we optimize this function. So they said they use Optuna, which basically use some kind of trial stuff. So this is an example where we have the objective and the trial, and now suggest float and suggest float also for X, and now return this. So when we run this guy, and now we have this objective function, now we can import Optuna, we can create a study, and now we can have call optimize on top of the study, and now we give our object that we create, and now we give the number of trials. So this Optuna will try to optimize automatically to find the base parameters. So you can see here is 0.1000 times. This is the last one. And now base parameters, it gave us these are our base parameters. So if we plug this back there, we will see that it optimizes that function. So we see that 1000 tries of 2.5 minutes to find the value of X that are reasonably close to the global minima of that function. So we can use that in our model as well, but we need for that number of iteration here we have, for example, we have number of try 1000, then we can use number of epochs, right? So train epoch and the alpha here, temperature, the temperature is integer here. So the trial, you can suggest float, you can suggest integer. So we need integer, but the alpha, we need some kind of float, you know. So this is that. And now this we can have these in our hyperparameter search on the DistilBat trainer that we train. Now here we have some argument called maximize. I don't actually understand why they put this maximize. They said because we want to best possible accuracy, we specify the direction equals to maximize and hyperparameter search. I don't know why this, anybody with, and now here you can see here the hyperparameter search, we put this function that will do automatically return the base hyperparameter here. I'm not sure anyone why this.
Yeah, that's fairly simple, right? You are trying to maximize, meaning increase the value of, so you're trying to increase accuracy, that is maximize accuracy. If, for example, another parameter like loss, then you would put direction is minimize, because you want to minimize the loss while changing the parameter. So that's just the reason.
Okay, so because we want to optimize the accuracy, then we put one. Okay, cool, thank you. So this thing takes like a whole bunch of time for me. I think this to try to find the hyperparameter while I was, because I started looking at the chapter today morning, and yeah, it was like, you know, taking time, you know, it takes a lot of time. And
at each step, he runs a training session. The training session is a couple of how you see iterations of batches. And if you would do say, if you say one training session would take 3 seconds, for example, and you would train it 1,000 times, you would already need or close to an hour to do all the experiments. So you have to make a lot of compromises here. If you use less iterations in the optimization, then you get a less precise output. So that you don't get such an optimal hyperparameters, but you get a faster operation. If you because over here you multiply all your training times the rounds which you do with optimization, things get very slow or not so accurate. So here they did 20 iterations. You see above here did 1,000. Over here they did 20, because you know if you do more than 20, then it's unbearable in time. So it's also and it's, I'm not sure how much it's comparable. If you say, well, with 1,000 iterations in a simple function, we got a very good result. So let's do it here with 20 iterations. I am not sure sort of how good these 20 iterations will really get us close to the best parameters, but maybe it gets us close enough to some good value that is reasonable.
Okay, so we can see like this is the best run, and we can see like we have these hyperparameters, and we can plug them, we can use them programmatically in, you know, find them KMB and now use them in our model. And yeah, and train the model as well as again. And now here we train the model with base parameters. And now we can see the student now, because we do hyperparameter training to select the base parameters, we can see now the student accuracy now increased to this, despite having almost half the number of parameters. So Sylvanus, here are here we are not using DistilBat, right? We are using the distill model because we are using this parameter. Is that correct?
Yes.
Yeah, because because
We
we
do
are
exactly
changing
the same
alpha
thing as
right now.
before.
Alpha is point whatever 0.24 or 0.1 something that you set instead of 1. So you are using the KL divergence loss as well
Yes.
as the student loss. So by that you are basically bringing in the teacher teaching, because by using the KL divergence loss, you're kind of making sure that the distribution of the student, the distribution that the student outputs, Q, is similar to the distribution of the teacher P. So by kind of using that loss, also because you have set alpha to a different value than 1. Do you follow what I'm saying?
Yeah.
In the previous instance, you had alpha is 1, therefore the second term was 0, so it was only the student loss. So it was just the Distilbert model without any teaching from the teacher model. Now, when you set alpha to the new value, and of course you also set the temperature, and then you run it for the number of epochs that it says you need to run it to. So here you see alpha is 0.138, whereas in your earlier run, you would have, if you print out alpha, you'd see that alpha is 1, which is the reason that the second term goes to 0. Because when it's alpha times 1 loss plus 1 minus alpha times the second loss, when you set alpha is 1, the second term is 0.
Are you saying in the previous round, we didn't actually do any distillation, we just trained the student on the data. We didn't, the student didn't take any benefit from the knowledge of the teacher, because at alpha equal to 1, he doesn't see the teacher. Is that what you're saying? So what I understand over here, initially I didn't pay attention so much. If it is true that in the example above, we had alpha equal to 1, and it means that the loss function doesn't take into account the teacher, which means we didn't do any distillation. The student didn't benefit at all from the trainer, from the teacher. Just he tried himself with the raw data, with the hard data, to come up with the best result which he has. But now in the second run, we give it quite a large portion of the data from the teacher, and so he can learn better based on the teacher. Is this what I? Is that so? If you say that in the previous example, because examples alpha was equal to 1, it means that we didn't do any distillation.
Yep. So it's just the basic. It is as if you're just using the Distilbert model on the data and finding out how best it does. And obviously, it's a much smaller model. It doesn't have the BERT-based capabilities. Therefore, you get some reduction in accuracy.
Which is
but here,
very small,
just
1%.
You're actually done.
So it's sort of over here, if you have a reduction of the scale of the precision just of 1%, which means that the model itself already is quite good. What I'm saying is that if you do without distillation, the small model itself gets already within 1% to the result of the bigger model. So it's not really they are both almost the same level of performance.
So the first one we did is already distilled silliness. The first one is already distilled. That's why it does have such close performance with BART. Is that correct?
No. The name of the model is Distilbert. That's what it's a smaller model. It's called Distilbert model. But there's no distillation we are doing to that model. We are just using the model as is, because when you set alpha to 1, if you go back and look at the loss equation, there are 2 parts to it. The first part is the student loss, direct cross entropy loss. The second part is the
in the book.
I mean, again, in your case of the slide, you have it set that way. But okay, let's look at the second last loss. So here you have self.args.alpha and then the cross entropy loss. It multiplies.
Yes.
So now think of alpha to be 1. When alpha is 1, the second term in the equation goes to 0. That means because, 1 minus self.args.alpha is 1. So that goes to 0 times the KD loss. So when you do set alpha to 1, there is no distillation going on because essentially you're just learning the cross entropy loss of, that is, you're just using the Distilbert student model as and as Yakov said, the point is the student model itself seems to be good enough to almost get within 1% of accuracy of the teacher model. And when you set alpha to 0.13 or whatever you find through Optuna, you now you're shifting most of the loss. If it is 0.13, then you're only making 0.13 times the cross entropy loss, and 1 minus 0.13, which is whatever the fairly large number, close to 1 times the KD loss. So this means now using the new loss with the new value of alpha, most of the loss is coming from the teacher teaching the student what the loss is. So therefore, when you do with a value of 0.13 of alpha and temperature of 2 and so on, then you've now found a distilled Distilbert model.
Maybe you can, if you go to the image with the 3 circles, maybe we can explain what's happening with if you scroll down to the graph with the 3 circles which we saw down. So I think what I understand now is
this one.
Yes, below. That's just 2. We have 3 circles below. So the way how this again. I think what's happening is what is the process of analysis. First of all, the blue circle is just the big model. So that's the baseline. You say we train the big model, and that's the baseline. We get a certain accuracy at a certain cost, a certain latency, for instance, over here. So now the yellow point is not distillation; it's another baseline. It says let's look how much the student model without the teacher would give us without distillation. So what's the baseline over here? Now you have 2 baselines. One is a bigger model using longer time and giving a slightly bigger performance. Then you have only the student without the teacher. You have a baseline which says it's almost the same performance, but it's faster. And then the third circle, which is the red dashed line, it says, where do we get if we combine both of these together? We take the smaller model, but we train it with a teacher, and we see that the speed is even faster. I'm not sure why this happens, but the performance moves up to the performance of the teacher.
So
it shows over here that only the last circle is so that the dotted circle is the first time when we actually try to do transfer distillation. The other 2 points are just baselines to say where would you get without distillation with a big model and with a small model.
Okay, I think I also get some understanding now. Yeah, thank you, Yakov.
I think so. Basically, what I learned from here, or what I see the example, when you do deep learning, you could try to come up with a wonderful plan how to do things and shoot immediately for the best result. So you get a certain number and you don't know what the number means. So that if you get 86%, is it a good number? Is it a bad number? Is your plan working or not? So what I say before we actually shoot for the result which you want to get, which is distillation, let's put the context where we are without distillation. So let's first draw this blue circle, which doesn't show us how distillation works. It just shows us where the model is. Let's draw the yellow circle, which shows us where the smaller model is. And you see the smaller model is faster, but it's slightly less good. So now when you do the distillation, you can see, yes, we got to the same speed as the smaller circle, we got to the same performance as the bigger model, and you would not expect that it gets even faster and even better, because that's all what it would get. But for some reason, it got actually faster than the previous student, and it got also slightly more performance and the better performance than the teacher. So that's interesting.
Yeah, so we can see here like the performance of this where we did the distillation is 94, which is almost. What I don't know, like, okay, benchmarking the distill here. Let's see. Okay, but also here the model size here. This is where we do the distillation, right? But it's still 255. So
it's the same model. It's the same size.
I thought we did this distillation here.
Yeah, but distillation, remember, distillation, Samsudin, doesn't change. It is the Distilbert model. So the model itself doesn't change and become smaller just because you have distilled. The model is smaller because the student model is smaller. So distillation doesn't reduce the model size. What reduces model size is your choice of a smaller model.
I see.
To use as a student model.
Okay,
so
then you take the
distillation reduces. Distillation only reduces, only changes the latency and the accuracy. The latency because you are now using a smaller model.
Yes. Okay, and you already learn some good stuff from the big model and you inject it now in the smaller model to increase its accuracy.
Exactly, because the smaller model doesn't have the same capacity. I mean, if you with all these transformer models, you have trillion parameter models. Now the Distilbert, and in fact, the other way to kind of hammer in your understanding is if you count the number of parameters of the BERT baseline model and compare it to the number of parameters of the Distilbert model, then you'll get the fact that the Distilbert model is much smaller than the BERT baseline model.
Yeah, so now I get it.
That's the reason the size reduces. So the size, obviously, in this experiment between setting alpha to 1 and setting alpha down, which is, just the teacher teaching the smaller model, is not going to change the size of the model.
Okay, so it is that we want to do distillation to select beforehand the model with small model, and we want to improve its accuracy and latency. Is that correct?
Exactly, and that is where the choice, they say in the textbook, is it's better to make the student model
of the same type,
the teacher model when you're making the choice.
So that's why we took the Distilbert here.
Yes, and that's also a BERT model. So, for example, what they're saying is you could use a smaller version of a Roberta model or a DeBerta model or something. And their comment is, don't do that. Choose, if your base is a BERT, choose a BERT-like model. So a Distilbert is BERT-like. So that's why the choice.
You see. I see.
I can comment on that I heard the same idea of distillation, but in a different context, where somebody actually suggested something different from using the same model. The story was that when you say you have a interpretable model, like you have a tree, for instance, like random forest or something, where you can explain why you got a certain result. And now somebody says you need to increase your performance even further, use a deep learning model. So you train the deep learning model and you get higher precision, but you lose the capability of interpreting the result. So you gain slight performance, but you lose your insight what happens in the model. And there somebody suggested you can do the same kinds of distillation to train the random forest or a tree, a simpler tree model from the training data, which is created from the more complex, like deep learning model. And as a result, the performance of the tree-based model can increase, but still it stays simple. So the idea of distillation or transferring knowledge from a complex model to a simpler model, does also work if the models are different. But the closer the models are naive, the more the transformation goes smoothly. So if you maybe lose more when you do this, but people still do this idea of distillation also between different types of models. So you can try it, and then sometimes it works.
Okay, so yeah, so now I get more understanding. So we can see here, I think this is where we stop to compare the performance here. They put the BART baseline, distill BART, and distillation, and we can see the distillation reached somehow the same level of accuracy. And yeah, the model size and latency remain essentially unchanged for the distill BART benchmark, but the accuracy has improved. So this is the point Sylvanus is making, and I now fully understand. So
before we go on to the next point, maybe I wanted to summarize over here something.
Yes.
You could say that you learned how to distillation, and you did over here a very specific sequence of steps.
Yep.
And I would say that this is just one example. What I mean by this, what we saw over here, it's something like transfer learning, but transfer in a different way. In transfer learning, you have the same model, and you have two different tasks. So you take a model which is trained on one task, and then you go to another task, and to transform some of what it learned on one task to the other task. Now, over here, for instance, if you do transfer learning, if you have a task of recognizing all different kinds of animals, and then you only want to recognize whether something is a dog or a cat, so you use the knowledge of them. Over here, we transfer knowledge from the same task, but different models. And in the end, what you do is you train the student model, the model which you want to work with in the end. You train it with different training data. You create better training data. So you could say, what we do now in our course over here, you said you can learn something by just reading the book. You can learn about the book by teaching it. You can make a presentation of it. You can discuss it with other people. And by doing different kind of, using a better training data, you learn more. The same thing happens over here. You use a teacher in order to create better training data for the student. And what we've seen over here is one specific way to do it from the beginning to the end. But every of the stages you can do differently, and you can create better training data in some way. For instance, if you have only very few labeled data, say you have a huge model which is pre-trained on a good task, and it can learn from just few examples the right distributions. But if you take a smaller model, because it's smaller, it is maybe not as efficient of extracting from a few data samples the right understanding. Okay, now you could do the following. You could take the teacher model and pass a lot of unlabeled data. And so if you have maybe a lot of unlabeled examples, and you create more training data in quantity, and you could go through the same process. So what I'm saying, okay, let's say again. In abstract, what we're doing over here is we just train the student model, the model which you want to use in production, and we try to give it better training data so that it's easier to succeed. So in our example, we gave it more insight from the teacher, essentially how confident the teacher is about things. And this helped the student to learn better, to deal better with the noise which is in the data and so on. But you could also do different things, like for instance, create more training data by running the trainer as a trainer on unlabeled data and create labels for unlabeled data so that the student has more data to learn from. And you can do many other things as well. So the message which I want to get on over here is that, say, if you're in a competition and you want to do distillation, so you could try as a baseline exactly to do what they did over here, but you still have a lot of room to move, to change things, and maybe to get a better solution for your specific use case by just taking the general idea to create better training data
for the student. And then, so you're not restricted to use exactly the same approach which is done over here.
Okay, cool. Thanks, Eva. Yeah, so I think that's all about the knowledge distillation, but we can make more. We can compress our distill model even further using the techniques called quantization. Yeah, so I don't know, like it's already time. We are over 12 minutes, and I need to hop on a call in 15 minutes. So I don't know what we can do. Can we? I don't know. We have.
A good idea could be to just do it next week.
Yeah. So maybe I think we can. Yeah. I will hop on another call. Maybe if we can finish the chapter next week. I don't know if it is fine with everyone. Then.
It makes a lot of sense because at one hand, we are at the right amount of time. And actually, well, it's distillation and quantization are two completely different ideas. So it's like two different chapters. So it's not that we are stopping something in the middle. We just finished one step, and now we start doing something else. So it makes a lot of sense if if everybody agrees to continue with the second half next week.
What do you think, other people?
Yeah, that's fine.
Okay.
Spend the time on it next week.
Okay. So thank you very much for joining.
You continue next week?
Yes.
Great.
Yeah, I continue next week with the quantization. Okay. Thank you all. See you next week. Bye-bye.
Bye-bye.
Thank you. Bye.
Thank you.